Welcome to the AI Cafe with Antonios Liapis today with his talk on, hi Antonios, great to see you, with his talk on AI and player experience. My name is Carmen McWilliams, I'm from Grassroots Arts, I'm your moderator and organizer of the cafe, and we both are part of the European research project AI for Media. And as always, welcome, great that you're all coming. Please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for Media project opinion. So what's the cafe about? As you may all know, the cafe offers a series of live web sessions, and it's an online forum to gain insight into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. So as always, this will be an interactive session. Please send us your questions, which you may have when you are listening to the presentation. I will afterwards read it to the speaker. And now we are coming slowly to the highlight. I will introduce the speaker. Antonios Liapis is a senior lecturer at the Institute of Digital Games, University of Malta, where he bridges the gap between game technology and game design in courses, focusing on human-computer creativity, digital prototyping, and game development. He received his Ph.D. degree in information technology from the IT University of Copenhagen in 2014. His research focused on artificial intelligence as an autonomous creator or as a facilitator of human creativity. His work includes computational intelligent tools for game design, user models for the design process, gameplay, or visual preference, as well as evolutionary computation and deep learning. He has published over 100 research papers on these topics and has received several awards for his research contributions and reviewing effort. He serves in the IEEE Technical Committee on Games and as associate editor of the IEEE Transactions on Games. So it's very impressive, and I'm very happy to have you here, Antonios. Once more, hello. I hope you're well. We heard you are in Malta, I think.
Yep.
So this is
shooting
really
on location,
exciting.
Carmen.
And now I will make you the moderator. The floor is yours. As soon as I give you the role, and then you may show and say whatever you like.
All right. Hi, everybody. I can't see you, but hopefully you can see me and you can see my presentation. So yes. Carmen gave me a really nice segue. I'm going to be talking about artificial intelligence and player experience. So I'm going to be trying to go a bit less technical and a bit more emotional in my talk. As Carmen mentioned, I'm not going to go through the list here, but I am at the Institute of Digital Games. I'm currently in Malta, and I am interested in essentially enabling the AI to understand and help humans, during their fun times or during their design times, both during, for example, game design. I'm going to talk about this in the talk, and also while playing. So this is it. You can find me on my website and on socials. We're going to be talking about basically how human designers craft games and towards which end. And hopefully at least half of you here are gamers, so you know that player experience is important. I'm going to be talking about what player experience really means and going a little bit more technical into what emotions are and how we can measure them. And then going into the meat of the talk, which is a number of projects that we do at the Institute of Digital Games on artificial intelligence for modeling emotion, emotion of players in this case. And I have left a couple of minutes in the end to talk about my institution, in case you're interested to visit us or collaborate. So with this in mind, let's dig in real quick. So let's talk about the game design aspect of, well, playing games. Game designers are, there's a debate whether they're artists or scientists, but let's just say they're very creative people that have to juggle a number of, sorry about that, have to juggle a number of creative disciplines, from art to architecture to audio to player experience, and we're going to get into that later. So games are an amazing domain to study in every aspect because they blend all of these things together. You have visuals because things need to be rendered on the screen. You need audio. You need narrative often. You have level design, which builds from architecture and urban design, game design, which are the game rules. And finally, you actually have the creativity of the players that introduce their own way of interacting with a game. So with all these things in mind, it's hard to do game design. Any game design, any aspect of design is essentially divination, right? You're trying to guess how someone else that is not you will use your software or your tangible object. Now, of course, design is not a new field. There's a number of ways of dealing with predictions of how people will use your software. Things like affordances and constraint, things like synthetic personas, and of course, in the end of the day, just asking normal people through small user tests and patches during the whole period of your game design process. But why does divination not work? It's a kind of a long discussion, but let's just talk about games now. Games are played by many different kinds of people, and I'm very happy that over the last 10 years, 20 years, the player base has become larger, has been more colorful, has been more diverse. It includes people that play for the competition. So there's people that play for to win, to gain money, esports players, for example. There's people that play to hang out with their friends, to network, to spend time with their family. Other people that try to recreate, fantasies in their games. So with all this in mind, it's really difficult to predict how all this broad set of people will perform. Interestingly, there's many players that ignore or misunderstand how you design your game. So they might use, what you put there wrongly, or they might actually exploit it. So here we have some examples of exploits which the designers didn't think about. Players might play subversively, so not play as the game designers intended, but play towards, use a virtual world, for example, to propose to someone else. They might play towards their own challenges. They might not care about what the game wants them to do, but they might put their own challenge, basically lower their own power, their own potential in order to win in a specific way. This can be also done for example, through trends in the community of gamers, right? And speaking of community of gamers, finally, in competitive games, there's a meta game that evolves, right? There's a strategy that may become very prominent and everybody starts following it. And then a counter strategy is invented to basically, win against this dominant strategy. And then this cycle continues and continues. So people find different ways of playing the game as we go. How do designers deal with this? They might deal with it poorly, or they might deal with it well. Usually they allow players to change the game towards their own preferences. They might patch the game to make sure it's more balanced. They might actually reward subversive play, but it's not easy dealing with how many different designers, different players interact. So where does AI come in? I'm going to touch upon this a little bit later, but first we need to talk about player experience and emotion. And again, I sincerely hope that there's a lot of gamers here, so that I don't have to explain to you why playing games is an emotional endeavor, right? We like playing games because they make us feel things. We are invested in this silly game. We feel, frustrated when we lose. We might play things like horror games that you see here, which make us scared, right? So again, playing games is emotional, and then now we need to discuss what emotions are. So going really quick through the theory, there's a number of theories about what emotions are, what kind of emotions there are here. And I'm going to be focusing on this part of the presentation, talking about the circumplex model, which categorizes emotions in two axes. One being valence axis, which is pleasant emotions such as joy and calmness, and unpleasant emotions such as sadness or anger. And the other axis, that of arousal, that splits emotions between activating ones such as anger and happiness, and deactivation such as calmness and sadness, right? These lower our arousal. The reason I'm mentioning this is because it becomes relevant when it comes to how we measure emotions. Now, you as a human, you have many ways of showing your emotion, right? That's often you understand how you feel by how your body reacts. Sometimes it's unconscious, such as sweating. So heart rate might increase. You might start sweating. Your facial expression changes. If you're happy, you're smiling. If you're angry, you know what you're doing. Your posture changes as well. And finally, there's also ways of measuring your brain activity, which triggers different parts of your brain when different emotions come into play. Now, there's a lot of work that has focused on measuring emotions on these, let's say, primary modalities. However, what we're working with, and we're obviously not alone, is actually what humans tell us regarding their feelings. There's a number of reasons for that. It's a bit less noisy. Now I can just ask you how you feel, and you can say I'm, through a drop-down list, angry, sad, etc. You might use a scalar value, such as the mannequin here. So between, 5 possible states of happiness to sadness, or you can actually compare between two different stimuli. So here we have an example where you see two videos and you choose which one better expresses satisfaction. The reason for this is that it is not as easy to have to tell you, I feel happiness 5, right? What does that even mean? Different people grade differently. I'm sure the academics here understand what I'm talking about. So here, when you're just choosing between two things, it's a bit easier. And there's always a neither option that allows you to basically say, this doesn't matter. They both express no satisfaction. The other question is, who is doing the annotation? Is it you, the person that has felt something, or is it someone else who is actually observing, the situation and impartially assessing the emotional state that they assess? The other dimension is when this annotation is taking place. How often do you actually annotate? Do you do it all the time? For example, every 5 seconds, someone asks, are you angry now? What about now? And there's obviously different ways of doing that. Or just at the end of a long period, then you get a summary and you essentially say, okay, I was feeling happy during this whole time, right? The other issue with emotion annotation, especially in tasks that are very cognitive, have a high cognitive load, is you cannot actually stop and then assess your emotional state while you're playing a high stakes game, right? Just as an example. So what we do instead, we we use a simulated recall technique, which means we show a video of you playing, and then you annotate that video a few minutes after you've played it. So you are remembering what you were doing and trying to remember also how you were feeling during that time. So these are our methods. Mostly, I'm going to be talking about comparisons between emotional stimuli, first-person annotation in our case, and then a time-continuous approach with simulator recall. All right, going into our methodology, I have two examples here in the extended version, and I'm going to be briefly talking about two other of our projects that are relevant. Now, as I mentioned before, oh, sorry, there's one more thing about AI before I go into actual projects. I want to talk about how AI sees emotion, and it's close to, on a very basic level, to how we treat emotion. We see a stimulus, like a scary monster in a horror movie. Our brain, or parts of our brain, processes this, and then we might smile or we might recoil. And if someone asks us, we might say that this makes me afraid, right? So the output is your bodily manifestation and your annotation after the fact. And the input, it can be a video, a music, a game, your grading experience with your students. All of these can elicit an emotion. The AI probably does something similar, right? Predictive models can learn input and output patterns on a training set. So you use a part of your data set to train, and then you predict the output of a test set that the model has never seen before. I'm going to be talking about two methods, two types of methods, deep learning and more old-fashioned AI, such as decision trees and SVMs. I'm not going to go into technical detail here about these methods. I'm just going to talk about the use cases where we apply them. So now, finally, sorry, we start talking about our own projects on this in this scope. As I mentioned before, games have many different creative facets, such as visuals, audio, narrative, levels, rules, and gameplay. And we will be talking about, in this example, how in-game sounds impact emotion. This was inspired due to our extended work on a specific project called Sonancia, which was trying to create complete horror games automatically based on what the designer intended, right? I'm not going to go into too much detail here, but it generated a level and then and then placed different background music in each room. And the idea was that in areas that had high tension, such as areas where the monsters were, the audio would also be more tense, right? Would cause more tension. So the audio would foreshadow things that were going to happen, or it might help to calm you down after you have run away from another monster. So the core question that we're trying to answer here is, which criteria are we using to place these sounds in the different rooms, right? The obvious option, at least for our first prototype, was to ask the PhD student that was doing this work to just manually rank all of the different background sounds that we had in our database according to their own opinion of what is tense or less tense. We would like to expand this, and this is why we hypothesized that we can crowdsource how people feel when they listen to different sounds. Unfortunately, I can't play the sound here because of the limitations of the medium, but they were mostly synth sounds. So they were very high-pitched synth sounds that you might hear in, for example, Blade Runner. So we wanted to see whether these kinds of sounds were tense and whether some people might think that sounds were less tense than others, and use these to train an AI model, basically, so that new sounds would also be classified, even if they were unseen by humans. In this work, we were looking both at the original, sound bites, or just to the at filtered sound bites, essentially applying a low-pass filter or different types of filters on top of them to create, variations of the sound rather than new sounds. All right, so the way this worked for our crowdsourcing experiment, we crafted our own sound library manually. We had a public user interface. I'm going to show in a little bit. We asked participants to rank sounds. We collected these in our database and then applied a rank SVM model to essentially predict the rankings of the users. The cool thing about rank SVMs is that we can then derive a global order by pairing everything against everything. So we can say this sound is the most tense, and this one is the least tense, right? In terms of our experiment, we had this interface, literally. We had two sounds that you could click on as many times as you wanted and listen to them. Then we had three questions. Is sound A more pleasant than sound B? Or both are equally pleasant, or neither of them are pleasant, right? And we obviously throw out these responses because they're not clear rankings. Now, which one creates higher tension and which one elicits higher arousal? So again, we're using the arousal and pleasure axis of the circumplex model. We collected 1,000 rankings through a number of participants. Some people evaluated 30 sound bites. Some people evaluated 10 or 2. So we collected a total of 1,000 rankings. What we did next to process our data, we actually used an existing tool for audio extraction that gave us 384 features, mostly focusing on the MEL frequencies and spectral information. And again, we processed the numbers that we got from the feature extraction tool to train our rank SVM model to predict the rankings that the users gave. What we found out when we tried to model tension, arousal, and valence is that valence was actually much easier to predict. We reached as high as 70-something accuracy in our rankings with a baseline of 50%. So that says something probably about the types of music we showed to the to our audience. A lot of them were very tense anyway, so we couldn't really predict tension very well. Similarly for arousal, because they were all scary, so therefore arousal was always high. But at least the valence axis was a valuable one. The uses of this kind of research is that now we had this model and we could evaluate new sounds that were never seen by the users, the crowdsourcing users, and we could even generate new sounds and then evaluate them in terms of effect and actually optimize a sound towards maximizing effect, for example. We also could apply different filters, since, as I mentioned before, we learned models also for which filters produce better tension. So then we could modify a sound easily towards increasing or decreasing its intended elicited tension, right, or valence. And finally, obviously, our original, for the purpose of Sonancia, we actually had a better model of choosing what sounds to put in each room. So it goes, I went from general to specific, but yeah, there's a number of applications of in-game sound and emotion models. But we're going to be talking about visuals now, and here we're focusing on what the user sees on the screen. So our hypothesis in this specific project is that what you see on the screen has enough information about the emotions that you're feeling while seeing it, while playing it, because of the rich interactive experience. So the context of your of your gameplay is enough, and therefore you don't need more complex biosensors for measuring your manifestations of emotion, your face changing, or your posture changing, or your skin conductance, things that have been tested in the past for affective computing in games. The way we collected our data, here's where the bunch of the buzzwords I mentioned before is in a first-person manner, in real time, in a video that was recorded of the same person playing. So you saw yourself replay a game that you played basically 2 minutes ago, and you were given this axis here, and your mouse wheel, through your mouse wheel, you could increase or decrease the arousal at the current time, and at the same time you could see the entire trace of this session. We annotated arousal only because we felt that this was a more meaningful dimension. Some areas were high-paced, some parts of the playthrough were more high-paced than others, so we expected that arousal would be higher in those areas. So through a single dimension of arousal, we collected data from 25 players in this fairly simple shooting game, which comes with Unity, and you're trying to shoot to survive against the onslaught of these cuddly monsters in a sort of nightmare scenario. The players first played and then annotated, and this repeated twice. So we had 50 data points from our 25 participants. Now, how we treated the data, because it's a very extensive set of frames and traces, we actually turned it into a binary classification. We wanted our model to answer whether a specific frame or a specific sequence of frames had high arousal or low arousal. To do this, we only cared about the relative values of these. So it didn't really matter whether you were not very activated during the entire time. We just cared that you were more activated during this period than during this period. So we split it based on the average of the arousal trace, and we remove any data points that were within some sort of ambiguity threshold. So here, because you might have just accidentally moved the mouse wheel or something, we just omit these data points. So we keep these data points for high and these data points for low, and the associated frames that go with it. We take these frames and we convert them into grayscale. We rescale them to make them smaller, as you might have guessed, and we process them through a deep learning architecture. The output was either high or low, so it's a binary classification, and we trained it on the training set and tested it on the test set. On the test set, our models could reach classification accuracy, again, high arousal versus low arousal, of around 77%, which was quite impressive. So that means that at least in terms of this simple game where you're shooting, shooting toys, and you have these particle effects, it's easy for computer vision to figure out which areas are high arousing and which portions of the video are low arousing. Interestingly, all the models that we used, either with frames, sequences, or video segments, all reached fairly similar accuracies. The cool thing about this work also is because we could use GradCam activation maximization visualizations to show which areas of the screen. So here you see all the time the score is a very good predictor of arousal. And the reason is that score keeps increasing. And when the score is increasing, the game has gone on for longer, and there's more monsters on the screen because there's like you've reached a higher level. Also, you notice that often when you're shooting, you see the particle effects or yourself as a predictor. So it's a very valuable tool, a bit difficult to make out, but a valuable tool for designers as well. They can understand this activation maximization. Now, in our next work, because as I mentioned, our first work was a simple game where you were shooting cuddly monsters, we wanted to see if this can span to different games. So we used 4 different games. Again, our shooting game, a puzzle game, a physics puzzle game, whatever you want to call it, a rally game, simple rally game. You were racing against 3 AI opponents, and Sonancia, which again is a horror game. It's super dark. It's and there's also interesting, scary sounds in it, discovered through AI, as I mentioned earlier. So we took the same approach. We asked players to annotate after their playthrough, and we used both the audio information and the frame information. We split it into frames that passed through a deep learning convolution, and we passed the audio through a filter that gave us 330 coefficients. This is just a standard library, and then we combine them into a fusion layer, and through late fusion, we try to predict the same thing, right? High or low arousal. And interestingly enough, with the combined, the visuals were actually quite good predictors anyway, but with the combination of audio, we could increase the accuracy a little bit more. Here you can see our test accuracy at different thresholds. We reach 80% or 70 to 80% in all our games, even with preference learning, which is another algorithm that actually learns more about the relationship between emotions rather than just high arousal versus low arousal. But Sonancia down here just does not work, right? And we hypothesized for a very long time. And in the end, the idea is that the visual information provided by Sonancia is not enough. Like there's not enough information, not enough context. This is the only game that doesn't have a user interface where you can see, for example, the score or things like that, which were quite helpful for other games, as I mentioned earlier here. You see in the activation maximization function visualization. So we learned something. It works for most games, but mostly for arcade games that are, high-paced, and there's a clear benefit. Like, oh, you're dying. Okay, that's a clear arousing state, or you overpassed your opponents. And for Sonancia, it really didn't pan out. And there's ongoing research on why this is the case and how we could do things differently. Again, you can use the same kind of visualization. The different methods return slightly different activation maximization maps, but the trends are the same. You're focusing on yourself and on enemies around you. Here in Maze Ball, which is a puzzle game, you're focusing on again the time left and on your opponents. If you see here, these are your opponents that are closing in on you. For the rally game, you're focusing on the goal and on the horizon. Interestingly, not on your car, because your car is always on the screen, so it doesn't really matter for your arousal state. And in Sonancia, I mean, you're focusing obviously on the small field of view that is available. But again, you can't really trust these visualizations because the accuracy is quite poor. Now, why did we do this? Well, we did this to find out if we could. That's the honest answer. But there's a number of reasons why this is a valuable kind of finding, because you could actually learn about what the players feel without having to pry on their, invade their privacy, right? You don't have to hook them up into, skin conductance sensors. You don't have to have their webcam open. You can just check out what they're playing right now, what their screen is right now, and draw some conclusions at some level of granularity, high arousal, low arousal, with a fairly high accuracy. If you're a designer, on the other hand, you can also use these GradCam visualizations to maybe identify which visual stimuli are triggers and fix those so that things that might be triggers, emotional triggers, be more prominent or less prominent depending on what you want to do. And for example, Sonancia, maybe add more elements there so that players can become more, more interested. Finally, We also wanted to check whether the visual feed could actually contain information that can be game agnostic, right? Visuals might change. If you change the color of the horizon, it's still an important aspect of your rally driving experience, right? That's where you're looking towards. So hopefully we're trying to do extra work that raises these models to be style agnostic. This is ongoing research that I'm not going to mention right now, but hopefully if I come again to the AI Cafe, I can talk about it in a couple of years, what came out of this. I want to talk about our other research, though, that is focusing on other creative facets. Here you can see just a preview of our work with Manuel Xilakis on architecture. So this is focusing on the level design and how that impacts emotions. To do this, we used recorded videos of basically a researcher playing through a number of generated rooms. Let me real quick replay this. And we asked a lot of people to annotate their arousal in these rooms and their valence. And we found out some interesting properties about what people prefer or people find more arousing. So curvature was always an important factor. Noise, how many columns there are and how much occlusion there is in the scene. So that's some of our current work on level design and emotion. You can see there the paper, you can read more about it. In the interest of time, I'm just rushing through our other projects. Here, this was a project about what I mentioned earlier, general models of emotion, to help ourselves and not worry about gameplay footage. We actually used gameplay metrics here. So this goes closer to the gameplay facet because expert game designers chose what data to log, things like in the rally games, distance travel, distance from your nearest opponent, whether you were on a bend or something. So we had 3 different games for 3 different genres, rally games, shooter games, and platformers. And we were trying to find out whether through the annotations that were treated in a similar way to the previous experiment, high arousal versus low arousal, whether we could predict emotion in an unseen game, such as this one, if our models were trained on these 2 games of the same genre. And we found some very promising results. I don't have the numbers right now, but we could actually create fairly general models, provided that our gameplay metrics that we were logging were clever. So this is still a bit more, old-fashioned. We're not taking the gameplay footage and extracting all the information. But if you have a game designer that knows what game data to log, that can be very powerful for your AI system. That's pretty much it for our projects. Again, you can read more technical details on my website or on archive. I wanted to talk a little bit about AI and player experience, which was my title. But the important thing is that we can use AI to improve the player experience as well, and to improve the designer experience when they're trying to guess what the player experience is going to be. It's not just done to see whether we could do it. It's actually useful. As I mentioned before, games can elicit powerful emotions, and that is done because the designers know how to trigger these emotions. These emotions can be due to the story, due to the visuals, due to scary sounds right behind you, or gameplay intensity, right? If something is very fast-paced, you become more excited, more agitated. It's useful for designers to know which of these aspects are impacting the emotional experience of players. So AI can learn effect patterns from the game setup. Basically, before you even play the game, the colors that the designers have chosen, the levels that the designers have crafted can be evaluated by the AI, and feedback can be given to the designers to maybe help them create a more suitable emotional experience. But it can also be gathered during gameplay. So by keeping the footage, here the video recording of the player playing, or logging the gameplay metrics, you can actually derive emotional, predict emotional states from only that information. And that can be a very powerful tool if you're a designer to, for example, know how your players, estimate how your players are feeling for a broad player base. This can help in general towards general artificial intelligence and also improve games while we're at it. One thing that I don't mention here and I wanted to touch upon is that the AI can change itself to personalize towards things that you find more interesting, more arousing, more frustrating, and give you more of that as well. So the game AI can change the game, your game, towards a more personal, tailored experience according to your own emotional models. So that's pretty much it in terms of the meat of the talk. I want to spend just a couple of minutes. By the way, I have no idea what time it is right now, but I'm assuming Carmen hasn't stopped me, so I'll keep going. I want to talk a little bit about my institution. So we're in the Institute of Digital Games. We got established in 2013. We're an independent institute in the University of Malta, where we teach master's degrees on game studies of any type, right? We have 25, actually probably more at this point, researchers and Ph.D. students that are focusing on both humanities and games, such as game design, game analysis, and technology in games, mostly artificial intelligence, player experience, affective computing, computational creativity, etc. We have 4 permanent staff in our AI subgroup within the IDG, and 3 postdocs and 7 PhD students. We are participating in many EU projects over the years. We've won several awards, and we generally try to publish as much as possible at highly relevant venues. All of the papers that I mentioned earlier have been published at Transactions on Effective Computing or IEEE Conference on Effective Computing. Finally, we do our research in terms of effective computing and procedural generation. We're not focusing as much on bots playing games because we find that these other aspects are also quite interesting and under-researched. We have kickstarted or assisted a number of EU projects, including a startup, an AI startup that is now growing and dealing with automatic playtesting and synthetic personas, very similar to the work that I've mentioned here. AI that estimates and plays according to an emotion. We've published over 200 papers in conferences and journals, and we also organize the Game AI School and other in-person or online dissemination. Some of it close to AI Cafe. Some of my own work is on doing some such community engagement events as well. So if you're interested in all of this or any of this, you can reach out to us or me personally. We have a Facebook, Twitter, and our website. If you're a student and you want to do a master's or a PhD, reach out to me. If you're a researcher looking for a cool sabbatical in Malta, it's very good this time of year, highly recommended. And with this, I think I'm gonna stop my presentation, stop speaking for a moment, grab some coffee and let Carmen take over.
No, you have to stay. Thank you, Antonius. No, we need you. This was a great presentation. Now we, of course, have questions, and then you can.
It's okay, I got my coffee with me, don't worry, I wasn't leaving.
Oh no, as I have to answer all these questions. So I start right away. It's super exciting for me to hear all these things. My questions is basically, I heard now that you basically do explicit measuring of the gamers. You ask them either by filling out like smileys, I liked it, I didn't like it, but you also have this kind of arousal measuring afterwards, no? That you basically say, oh, I see my own recording, and then I can say this is how I'm aroused. Yes, my question here is, isn't that a little bit self-fulfilling prophecy? Basically, an arousal is when you have a lot of monsters, more monsters coming and more monsters coming. But what about other games and monsters or car driving?
Mhm.
Can this be used, your tools, for other games which are maybe more like, I mean, now in dancing games or in
Mhm.
sport games? Is it
Um,
also applicable?
Right. I'm pretty confident about dancing games, by the way, but because they're very high paced, so it's easy to actually just guess from the pace that the player is dancing, or other people are dancing around them, or the context of the music, that you could actually model emotions, because we've done this in music and emotions that I mentioned earlier. Measuring frequencies and how they impact emotion is, I'm not saying it's a direct science, but I'm pretty confident that you can derive some model with a good accuracy there. The more important question, I'm gonna shoot myself in the foot and tell you how um, how the sausage is made. The reason why these games work is not because they have monsters. Sorry, I'm trying to find the games actually. It's because they are short arcade games. So you only play these for 2 minutes, and then you stop, and then the recording is shown. Regardless of whether you were progressing and having fun and wanted to play more, you can only play for 2 minutes before it's time for you to annotate, right? And also these games usually end after 2 minutes. They're designed that they're not super long experiences. If you're playing role playing games, for example, that takes a long time. It requires you to read a bunch of things. You spend a lot of time leveling up. These games are not that. I feel that games that are longer, that take longer, they don't work for our methodology of either simulate a recall, because you would need to watch a whole hour of you playing, and also because the changes in emotion are much less clear, right? Like you don't
Yes.
really you don't feel very aroused because you met someone and you started a discussion with them. It's much more long term. You would need a completely different protocol that we currently do not have. So this protocol works for arcade games that have fast action, and the action finishes quickly. So that's my take. Dance, on the other hand, is also a fast-paced activity that does have a short duration unless you're you have very good stamina. So I'm still confident that this is probably a problem that our method, let's say, can solve.
Yes.
Famous last
Great.
word.
Great. Great. So I'm coming back to this after this coffee.
Mhm.
And then here, questions from the public, from the audience. Here we found Baptist. Let me just get it a little bit nicer, because there's a long Baptist one. I want to say everything what he said. So he said, Baptiste is said that, I'm so sorry that you could not share the sounds. Could
Yeah.
you please talk a little bit more about it? Are sound real music? Could the algorithm works for music? I heard that although AI can be used to compose music by a composer, it is still far from being able to compose all by itself. So,
Well, let me
long.
tell you, let me tell you that AI that composes music is an ongoing, very interesting research in computational creativity and beyond. It's not there yet. You can say that. I'm sure some of my colleagues might disagree, but the AI can probably compose the music that we were using, honestly, because it's synth sounds, that's slow transitions. You can actually use tone heads, which is just a random walk algorithm to shift between sounds. So they were there were staccato sounds, for example. It was mostly filtered sound through a synth. So it wasn't a Bach chorale, is my point. So I'm pretty sure that an algorithm could create something like this. Even if the algorithm couldn't, by the way, we also explore just the algorithm applying handcrafted filters to existing sounds. So even if you don't want to rely on your algorithm that you are not sure if it's generating good enough things, you can use a filter and then apply a low pass filter or the distortion filter or both to create something that is more arousing or more tense or more pleasant or less pleasant, etc. So there's different degrees on what you can do with this, depending on how much freedom you want to allow to the algorithm and how much you trust the algorithm in terms of its output. I hope that answers vaguely the question.
Yes, great. For me, at least. And Baptiste is not coming back. So if Baptiste has more questions, you have to tell them later. Here comes Yasmin. Yasmin, hi Yasmin. Very interesting work. Thank you for a great presentation. I was wondering about that you said a game could adapt to the particular player. If that is the case, wouldn't that be the chance for social interactions of players of the same game? For example, in a group of friends, each plays the same game. They usually discuss it and help each other, maybe by giving advice, how to clear a level or opponent. So the question is, wouldn't that the chance for social interaction?
Let's just say it's not the first time I've heard this question. It really it's a great question. Thanks, Jasmine. It clearly needs a specific type of game and a specific type of player, right? If you are playing a social game which actually has built-in user interactions such as World of Warcraft, you obviously can't personalize that. If you're playing a competitive game that relies on you being on the same level, you cannot adapt the game because that will be unfair to the other player. However, yeah, and I know that you were talking about single player games, and you can have these water cooler discussions of like, oh, how did you solve this level? And if the solution is different from one player to the next, that's not a lot of fun. But a lot of games out there have generation anyway. So a lot of games you play, such as roguelikes, you play a new level, you play a random level, and then you just every day you might play a new generated level. I have 1,000 examples, but again, Rogue, Diablo, all these games use generation, Civilization, all these games, they generate new worlds. So there, you can discuss meta strategies rather than the specifics. So if you generate different things to increase either the emotional response of the player or just to make it easier for them or more challenging for them, the meta strategies that you can discuss over the water cooler are still maintained. But yes, you're right. You will not say, oh, just go left when you see the tree, because there might not be a tree, there might not be a left, there might you cannot use this in games that are very, very structured. I want to point out actually real quick, I know you had this in one of your questions, Carmen. There's games that do use these kinds of challenge models to adapt their games. So Left 4 Dead, for example, which is a very famous and successful game, it changes the game slightly in terms of how often zombies emerge or how big the zombie hordes are, without changing really the experience. So you can still have a discussion with your friends about about this level without really changing like it's not a completely different level is my point. All right, sorry, I spent a lot of time on this.
Thank you. It's called Left 4 Dead?
Left 4 Dead, yes. Yeah, Left 4 Dead 1 and 2. Yeah, it's a great game.
Okay. Good. The question was, as the audience didn't hear it, was I had before was do you know an example of an existing game where the emotions of the player are measured in real time and can influence the gameplay in real time, basically? And here we are, Left 4 Dead. I'm checking it out.
Yeah. So about emotions, yeah, it's not about emotions. This one is actually just measuring the challenge. So how well and how relaxed, how the pacing has been so far. So if you are full on ammo and you're still healthy, then the monsters become more dangerous or the hordes become more faster, etc. So real-time emotion detection, I don't think of a very famous commercial game right now that does this. I know there's a few of these, but I believe that they were only using models during testing and not actually deploying, having your webcam shown, or, for example, to measure your emotion. So there's no game yet that comes to mind that is famous that does this. The emotion bit, the challenge bit, yes. Quite a few games do that.
Yes. Okay. So I hear this. And now another question from the audience. And Nicholas, Has someone identified or categorized different game design patterns that elicit particular emotions? Do you know about this?
Where do we start? There's there's a lot of work, especially on horror games, for obvious reasons, because horror games are, they're designed to just elicit emotions. There's a lot of work that's focusing, for example, on the visuals, on the rendering for such kind of games, horror games again. There's level design patterns that that have a strong effect. But yes, there's a number of studies that focus on the design aspects and how the design can impact emotion. I can't really, there's some of the work that we do is essentially validation of that, because, for example, in this work, we used the literature on what is important. Yeah, okay, it works. What important design features are, and then we try to measure how these design features impact emotion. So there's a bit of work there. There's quite a bit of work there. I strongly recommend looking into horror games for the most relevant literature there.
We come back to the monsters.
Yeah, well, it's a personal favorite. What can I say?
So we are coming slowly to an end. One more last, Alan. Have you considered using neurofeedback mechanisms, reading brain waves to act as calibration mechanism?
No. There's a variety of reasons. I'll tell you why. I'm not going to tell you all of them. Basically, I am not convinced, and in our lab, we have not managed to use biosignals particularly well, especially when players are playing games. We've tried to have players play games so differently that it's tough even with posture or facial expression. And for example, some players, express their anger during a game, and others, like myself, they're so focused that they're just completely stone cold. So even simple things like facial expression, which we kind of understand more than brainwaves, just because we are humans and we see other people get upset and visually get upset, right? We've used skin conductance in our past work. Again, we had problems with people moving too fast and too much because they're scared or they're using their controllers. So that had also a bit of noise. Brain activity we have not even tried because it's scary. But I feel that it might be too challenging to have someone in a cask also playing a highly engaging game. The cask will move a lot, and then you will have very noisy feedback. We did some other work on a serious game on rehabilitation using brain activity, but not for explicit emotion modeling, not the kind of things like arousal that you saw here. So it was a bit more of a control mechanism rather than an actual input to our models, if that helps.
Yes. Okay, and it's rather invasive, as we learned from your presentation, and we all know. I mean, who wants to have that, really? Scary.
The applications are limited, let's just say. If you're a commercial game developer, the applications are limited.
Yes. So we are coming to the end. There was the last, the Eugenio asked once more, come back to your contact information. Maybe you're so nice, and once more scroll back to your contact information. Yes. So if somebody afterwards wants to get in contact, I asked Antonius, and he said it's okay.
That's why I give this presentation.
Yes. So if you have further questions, then please get in contact, or more, we want to network. And at the same time, there will be a recording which I send now afterwards to you, Antonius. You decide, completely free, if you want to publish or not. And if yes, then it will be on the AI Cafe recording, video archive, and on the AI for Media website. So, and thank you very much. And this was very enlightening. I myself will probably come back to you sooner or later because it's very close also to the dancing carousel project I'm involved with. And this is also the idea of this cafe. So if you went network, and you have new ideas, please come forward. And thank you. Have a nice afternoon. And Antonius, I will invite you back. You promised in some years you have more results. So
Hopefully less than a few years, but yeah, I'm looking forward. It was really fun.
come
Thank you
back.
everybody for thank you everybody for your questions. They're really cool.
Okay, bye bye. No?
Ciao.
Bye bye. Thank you.